Construct and interpret confidence intervals for the population mean. In a previous video, we covered the central limit theorem, which is a result regarding the distribution of the sample mean. I'll link that video in the description. Feel free to watch it as a prerequisite to today's topic. So we know that our sample mean x bar should be close to the population mean mu. In fact, based on the central limit theorem, if the sample size is sufficiently large, then the sample mean will follow a normal distribution with mean equal to mu and variance equal to sigma squared divided by n. Sigma squared being the variance of the underlying population from which you are sampling. And the variance of the sample mean is strictly less than the variance of the population for sample sizes greater than 1. That's because averaging reduces variance. Now, for this result up here, if we go ahead and standardize, what we end up with is x bar minus mu divided by sigma divided by the square root of n follows a standard normal distribution. Now, if we choose the 2.5 and 97.5% quantiles, then because the area under the normal curve between these two endpoints is equal to 0.95, we can write that 0.95 is equal to the probability that this quantity is between negative 1.96 and positive 1.96. And if we go ahead and solve this for mu, I'll let you do the algebra, we now basically have a way to trap mu. So we're saying that the probability that mu is between these two quantities is equal to 95%. Now, that's not going to be exactly how we interpret the confidence intervals, but for the purposes of us deriving the confidence interval, this is the way that we want to think about it. So based on this, what we have is that a 95% confidence interval for mu is equal to x bar, the sample mean, plus or minus 1.96 times sigma divided by the square root of n. So in general, if you have a sample statistic, x bar, a measure of uncertainty, the standard error, sigma divided by the square root of n, and a distributional result, which comes from the central limit theorem, you can construct, comes from the central limit theorem in this case, you can construct a confidence interval. And the general formula for the confidence interval here is going to be x bar plus or minus z sub alpha over 2, which is an endpoint chosen from the standard normal distribution times the standard error. Now, a limitation of this is that we likely won't know what the population variance is, so we would need to estimate the population variance sigma squared with the sample variance s squared. And if in this quantity we replace sigma with s, it turns out that that actually follows a t distribution with n minus 1 degrees of freedom. A t distribution looks pretty similar to the normal distribution, except that it has heavier tails, so you would expect more extreme values. But as the sample size approaches infinity, the t distribution will converge to the normal distribution. And this would be the general form for the confidence interval using the t distribution, which would be x bar plus or minus t sub alpha over 2. That's the endpoint chosen from the t distribution, times our estimate of the standard error, s divided by the square root of n. Now, when it comes to interpreting confidence intervals, the correct interpretation would be, for example, if it's a 95% confidence interval, we'd say with 95% confidence, we estimate that mu is somewhere between whatever the lower bound is and whatever the upper bound is. Now, using the word probability is not correct when it comes to interpreting these intervals because, for example, let's say that mu is actually 73, and we calculate a 95% confidence interval, and we find it to be between 65 and 72. There isn't a 95% chance that 73 is in the interval. It's a yes or no question. The correct way to think about it is if we were to calculate 100 different 95% confidence intervals for mu using 100 different samples from the same population, we would expect 95 of them to contain the mean mu, and then the other 5 would miss. And we're actually going to go ahead and demonstrate this. So we're going to iterate 100 times. Each time we are going to take a sample from a chi-squared distribution. Mu in this case, we are going to set it equal to 10. And we're going to calculate the lower bound of the confidence interval, the upper bound, and then we will append that confidence interval to our confidence intervals list. And then we're going to go ahead and plot the result. So if our interval does not contain 10, we're going to color it red. If it does contain 10, we'll color it green. So if we look at the results, in this case we have 100 of them, and what we see is that 95 of them, actually in this case exactly 95 of them contain mu, which is 10, and the other 5 miss. And mu is given by this purple line right here. So as long as the purple line passes through our plot of the interval, then we color it green. Now obviously from one simulation to the next, this will change. In this case, it'll cover 97, 3 will miss, and if you keep going, you'll just get varying results. But the idea is, on average, we would expect 95% of the intervals to contain the population parameter that we are interested in.